Hi, welcome to this lecture on mathematical methods for biologists. Today's topic will be integration. So, what is integration? The question that we will try to answer in this section is how to find the function if we know the slope. Right? We know the slope. If we know the slope, can we find out the corresponding function? We learned in the derivative how to find out the slope given the function. We are asking here an opposite question, how to find the function if we know the slope. So, that is called integration, and there will be a series of lectures on integration, and today will be the first lecture on integration. So, to understand this, let us recollect what we knew. We knew the function f of x, and we calculate the slope df by dx. So, this is what we find differentiation, which is the finding derivatives. So, this is the derivative. Now, we are asking the opposite question, that if I know, we now know how to calculate this if I know this. So, this arrow we know how to do this. So, this is finding derivative, right. So, this is something that we learned, finding derivative. We know how to finding the slope, right. We are now going to, so this thing is the slope. Now, we are asking the opposite question, that if I know this slope, can I get this? How to do this? From here to go to here, how will we go? That idea is integration. This is called integration. So, let us think about this a little bit from whatever we know so far. So, what do we know so far? Let us think of some curve. So, let us say we know the slope. So, we wanted to draw a function. So, let us say we know slope is equal to 3, that is, this is m, which is also called df by dx. So, we know the slope, which is a constant, which is 3. Now, the question is, can we draw a curve whose slope is 3? So, the question is, can we draw a curve whose slope is 3? Can we draw a curve whose slope is 3? Now, this is very interesting question, because let us think about it. We know if you have just slope as a constant, we know that it is going to be a straight line. So, we know that this answer, the curve is going to be a straight line. So, can we draw a straight line with slope is equal to 3? That is what the question will boil down to. So, let us think about it. So, what do we want? We want to draw. So, what do we know that slope is equal to 3? So, we want to draw a straight line with slope is equal to 3. This is what we have to draw, and let me try drawing this. So, I draw a line, this has slope is equal to 3. So, I can put x values and y values, and correspondingly I will have the slope which is 3. But I can draw another line. So, this could be the answer, this could be an integrate. If I integrate this function df by dx equal to 3, if I just integrate df by dx equal to 3, I will get this slope, I will this curve. So, this is an answer to this. This is the integrator of the f is this. If this is f, this is df by dx equal to 3, this is my f versus x curve. But I could also draw another curve, another straight line which is parallel to this. So let me draw another straight line which is like this, which is parallel to this. So pardon me if it is not parallel fully, but draw another line which is essentially parallel to this. And you will find that this also has slope is equal to 3. I can draw another line which is also parallel to this. All of this I can draw another one here. All of this will have slope which is 3. In other words, I can draw many functions. F is equal to 3x plus some constant c. I could take here my c, the intercept was 0, here the c was 1, here the c was 2, here c is 3. I could draw with c being minus 1 and so on and so forth. So I could draw this function f is equal to 3x plus 3. I can draw many infinite curves essentially by changing the value of c. All of this will have a slope which is my slope here. All of this will have slope is equal to 3. So what are we understanding? If I just specify slope alone, I can draw the shape of the curve, but I would have many curves. I would have essentially infinite curves which has slope is equal to 3. So by staying slope, I can get the shape of the curve and curve, but to get the precise curve, I have to also get an extra constant which is c. So if you tell me the slope and a constant, right, you have to tell me two things. If you tell me the slope and a constant c, I can point out precisely one curve. If slope is 3 and c is 0, then there is only one curve which is this. So this is c equal to 0. If c is 0, then there is only one curve. If c is equal to 1, so this will be the curve. This will be c equal to 1, this will be c equal to 2, this will be c equal to 3, c equal to minus whatever. This is c equal to 0, this is c equal to minus 1. So if you tell me a c value, which is the value here, the y-intercept, and the slope, I can get you this function. So this is so essentially integration is drawing these curves if I know the slope, right? If I know the slope, how to draw these curves? So we realize that it's not enough to know the slope. We have to also know the slope plus a constant. It's called a constant of integration. Now we will take an example which is relevant for biology. So let us take the example of polymerization of a filament called polymerization of actin. So this is, consider this actin filament, which is like a filament like this, and we have a monomer, which is an actin monomer, polymerizing with a rate Kp. Kp is the rate of polymerization of actin. And the actin will also depolymerize, let us assume, with some rate Kd. So this is a phenomena which is typically very well known in biology. Something will polymerize, something will depolymerize. Now the question is, how does the length of this actin would change? So what we want to know, by polymerization and depolymerization, what would happen? The length of this actin filament would change. Either it will grow or shrink depending on this rates of polymerization and depolymerization. So the question is, how can we describe this phenomena using the language of mathematics? So the phenomena that we have to describe is polymerization and depolymerization of actin. You have actin, and this gets polymerized with some rate, depolymerization with rates, and as a result of polymerization and depolymerization, what happens is length changes. Length of actin changes. How do we write? Changes with what? With time. So how do we write this mathematically, that the length changes? So we can write dl by dt, the change in length. So here the L could be the average length. Okay, if you do many experiments, L is the average length. So, how does this length would change? Right, dl by dt, the length changes with time. What is this dl by dt? If I know, if I could dl by dt is equal to something, that is an equation that is a mathematically telling something about the rate of change of length. So, let us see what can we write. So, if you have actin, we have to compute the change in length as a result of polymerization and depolymerization, and this is the equation that one can write. dl by dt, the length will change with if the polymerization rate is high, the length will change with the positive, this will increase, and the change in length will be negative, that is the length will decrease if the Kd, which is the depolymerization rate, is very high. So, the rate of change of length dl by dt will be Kp minus Kd. This is something that we can know. So, what we would know, dl by dt will be equal to Kp minus Kd. So, this mathematical idea, this fact that dl by dt is Kp minus Kd, this is called a differential equation. So, if you have this equation, this is an equation having derivative, right? Differential equation is an equation which has a derivative in it. So, if you look at this equation, dl by dt is equal to Kp minus Kd, this equation involves a derivative. So, this is the one of the simplest differential equations you can think of, and we want to know the L versus T. What is the length as a function of time? That is what we want to know. If you want to know the length as a function of time, we have to integrate this equation. We have to solve this differential equation. We have to, so this is essentially the slope. If you think of dl by dt as a derivative, Kp minus Kd is the slope, which is dl by dt. So, if I know the derivative or if I know the slope, can I know the L, right? So, this is, think about it, what we know, we want to know L versus T, and we have some curve, and this curve could be here, or it could be here, or it could be like this, or it could be any curve. We do not know what the curve is, but there is some curve L versus T. Its slope is dl by dt. So, this is Kp minus Kd. So, if you assume Kp and Kd are constants, so let us say Kp is 5 per second and Kd is 3 per second, Kp minus Kd is 2 per second. So, this is 5 minus 3 equal to 2, the unit is per second. So, if I know 2 monomers per second, 5 monomers per second, 3 monomers per second, so what is here? Kp is 5 monomers per second is the polymerization rate, Kd, let us assume, is 3 monomers per second is the depolymerization rate. If I know these two numbers, Kp minus Kd is 2 per second. So, if I know that dl by dt is 2 per second, this is dl by dt is 2, I know that the slope is 2, I have a straight line. But as we know, it could be any straight line, it could be various straight lines, there could be infinite lines which has slope is equal to 2, just like we saw just now. So, how do we now get the precise straight line, precise curve of actin length versus time curve? How will we get it? So, let us look at here. What we know dl by dt is Kp minus Kd. I could write dl is equal to Kp minus Kd times dt. I take this dt this side and Kp minus Kd dt. Then I could write length L as an integral. This symbol is called an integral symbol. So, integral dt times Kp minus Kd with this symbol integral. So, this is the way one would compute this integral. So, what do we know? If we know the derivative of a function, can we say something about the nature of the function? If we know the slope of a curve, Can we say something about the nature of the curve? These are the questions that we are trying to answer. And in general, just like we saw, if we know the slope, which is dy by dx is m, where m is a constant, we can integrate this equation and get y of x. In other words, if you have dy by dx is m, dy is m dx, I can take this way and write integral dy, put this integral sign on both sides. Integral dy is same as integral m dx, and y is mx plus a constant. This is that constant which we have to know. So, we have to know the m and we have to know the c, where c is an arbitrary constant, and this constant is something that we have to know. Now, let us come back to this example of dl by dt and see what we would get. So, let us take this example of dl by dt. So, what we have? We know dl by dt is Kp minus Kd, where Kp minus Kd is a constant. So, in other words, dl is equal to Kp minus Kd times dt. So, I can integrate this on both sides. So, that is, I put an integral symbol on both sides. So, then if I integrate this, I will get L here, integral of dl is L, and Kp and Kd are constant. So, I can take out this, I can keep, just like since this is a constant, I will keep Kp minus Kd as a constant like this, and integral of dt, then what I have is integral of dt. This is what I have. So, which is L is equal to Kp minus Kd, integral of dt is t. So, integral of dt is t. But this is not enough, I have to know as an extra constant. So, that constant I would put as c. So, Kp minus Kd times t plus c. So, that is L. So, the length of action at any time t, if I know the time t, even if I know this constant, I can calculate the length of action at any time from this. Assuming Kp and Kd are constant, I can get this kind of a formula. So, Kp minus Kd times t plus c is my length of action at any time t. Let us think about this a little bit more. So, what does it tell me? So, let us understand this. This says length at any time t is, if I know these rates, the polymerization rate and depolymerization are constant, times constant. This c yet we do not know. We know Kp, we know Kd, and we put it as 5 and 3. So, I will put 5 minus 3, this is 5 3, right. So, this is essentially 2. So, I can know L of t is 2t plus this constant c. Now, we do not know c. What is c? So, if I look at this equation and put t equal to 0, right, so if I substitute t equal to 0 at t equal to 0, length L0 will be 2 times t, which is 2 times 0, which is 0 plus c. So, L0, c is nothing but L0. So, what did we see here? We saw that the constant which we did not know is nothing but this thing is initial length. So, this is a physically meaningful quantity, the constant c. In this example, will turn out to be the initial length. So, if I know the slope, which is the speed of growth, so Kp minus Kd is essentially the speed of growth, and the initial length, I can know the speed of actin, the length of actin. So, this says that I can know the length of the actin at any time t if I know the speed of growth v, which is Kp minus Kd, plus the initial length L0. So, this which comes from this idea of integrating or by calculating the integral of a function, any function, or the integral of this particular function, which we said the rate of polymerization. The same thing is applicable for many other things, like imagine that you have a molecular motor walking along the microtubule. So, imagine the following, where you have a molecular motor. So, you have this is a microtubule on which you have a molecular motor walking. And what we know? We know that the position of this motor L or R is the position of this motor, changes with time, and we know the speed of the motor, V is the speed of the motor. So, if we know the average speed of the motor, this is the equation that we will get, dr by dt is equal to V, and we could write this immediately. This would imply that dr is equal to V dt. I can integrate on both sides. If you assume V is a constant, I can take this outside the integral. I could write dr is equal to V integral dt. This would imply dr is equal to V times dt. This would imply, this would immediately give us R at any time t is integral dt is t, Vt plus a constant. Now, what is this constant? If I put time is equal to 0, there will be R0, this constant will be initial time. So, this constant will turn out to be the initial position, the constant will turn out to be the initial position. So, I substitute R0 will turn out to be C, because I substitute t equal to 0, I will get R0 is 3. In other words, the full equation will turn out to be R of t is equal to Vt plus R0. So, if I know the initial position of the motor and if I know the speed of the motor, I can calculate the position of the motor at any time t by this simple integrating this function. So, the point to remember in general is that any function, if you want to integrate, in general if you have dy by dx is some slope that we know. So, this is something that we just said, that you have dy by dx and we know this slope. We can write dy is equal to m dx. I take this side and integrate on both sides. And if m is a constant, I can take it outside. That means, I can write dy is equal to m dx, and if I have this, the integral of integral of dy is y and integral of dx is x, and I have to have an extra constant, and this constant will turn out to be y at x equal to 0. In this particular case, c will turn out to be y at x equal to 0. If x is time, it will be initial time, initial position. If this could be initial position or it will be boundary at a position at a particular boundary. So, this particular thing typically would be called an initial condition or a boundary condition. So, this will be either an initial condition or a boundary condition. Why do we call it the boundary condition? Let us think about this in terms of, not in terms of time, but in terms of concentration. So, let us take, we want to write an equation for concentration. What we know, let us say we know that dc by dx is equal to 3. some number. If I integrate, I will have dc is equal to 3 dx. Since 3 is a constant, I can put integral sign both sides. I would write c is equal to 3x plus, this is a concentration. So, I would write some other constant k1 here, this is some constant k1. Since I already used c for concentration, here c is concentration. So, I know the concentration along x. So, this is my x. So, what do I have? This answer tells me this is c of x. If I tell the position x, I can know the concentration. If I tell specify x, I can get c at any point x. The given that I know k1, what is k1? K1 will turn out to be k1 is c at x equal to 0. So, what is x equal to 0? This is x equal to 0, let us say. So, if what do we know? I am telling you that the change in concentration dc by dx is constant everywhere. If that is the case, and if I know the concentration at x equal to 0, which is k1, if I know this k1, I can calculate the concentration at any point by using this formula, by integrating this, and this concentration is the concentration at the boundary, at this boundary. Since that is why often this is also called a boundary condition. So, at this boundary, if I know the concentration, so if I just say that k1 is equal to 0, if the k1 is equal to 0, the boundary, the concentration is 0, and the change in concentration is 3, I would get the concentration at any point x as 3 times x, if the concentration at 2 as 3 times 2. So, to summarize, we learned the basic idea of integration, right. Integration is basically, so what we learned, the first idea of integration, basically how to find the function given this slope or given a slope. Given a slope, how to find the corresponding function. We know that it is not enough. We also need to know, an extra constant, of integration. This is called a constant. So, to do integration, we have to know the slope and an extra constant at least, so that we can calculate this. So, this is the idea of the first lecture on integration, and we will learn more about this in the coming classes and understand how to think about any function given the slope and these constants of integration, and how to think about these constants of integration and how is it useful in various contexts in biology. With this, I will stop today's lecture.